In today's lecture, we are going to study the offset of differential amplifiers and see how to extend it to op-amp offsets. So let us take the simplest possible differential amplifier, which is a resistively loaded differential amplifier. Let us assume that the load resistances are R, the two transistors are M1 and M2, and the two currents are ID1 and ID2, and the two outputs are VO1 and VO2. Now this as a block diagram can of course be represented in this form, and if you were to represent the offsets in the circuit, the mismatches in the circuit as an offset voltage, you would do it as a series voltage source, and by convention we would use the signs so that a positive voltage needs to be applied. Now remember, just a reminder, VOS, the input referred offset, is defined as the voltage that needs to be applied to your amplifier such that the output offset is 0. So now let us do that. So we will assume that the two resistors are RD1 and RD2. We will assume that mismatches exist in VT, W over L and RD. So nominally the two resistors are RD, but in reality they are slightly different. We will also assume that mismatches are small. So these are the two assumptions in our analysis. So now we will say that VT1 is VT and VT2 is VT plus some delta VT. So it is slightly different from VT1. And we will say W over L of 1 is W over L, W over L of 2 is W over L plus delta W over L. Finally, RD1 is equal to RD and RD2 is equal to RT plus delta RT. These are our assumptions for this amplifier. Now we want to find out if you take such a circuit, you want to find out the input voltage that needs to be applied such that the output voltage offset is 0. So now let us complete the circuit in that manner. So I have an input offset voltage that is being applied. So this is the offset voltage that is being applied to the circuit, and we know that the output offset is 0, so we know that VO1 minus VO2 is equal to 0. Now this clearly means that the VDD minus ID1 RD1 should be equal to VDD minus ID2 RD2, and this clearly means that ID1 RD1 should be equal to ID2 RD2. So this is another fallout of the definition of offset. Now let us write down the expressions for offset. So clearly, if you go through the circuit, VOS should be equal to VGS1 minus VGS2, and this is clearly equal to root of 2ID1 mu n C ox W over L1 plus VT1 minus root of 2id2 mu n cox w over L2 plus VT2. We are going to rewrite this expression as root of 2id mu n cox w over L minus root of 2 into id plus delta I mu n cox into w over L plus delta w over L plus Vt1 minus Vt2, which happens to be delta Vt. So let us now take this expression out of the brackets as a common factor. So this would be, the second factor would be 1 plus delta id over id over 1 plus delta w over L over w over L. So please note that this particular term here represents the nominal VGS minus VT or VD sat of the device. So this is the nominal overdrive of the devices. So now let us simplify this further by using the following assumptions. We know that the mismatches are small, therefore delta ID by ID is much less than 1 and delta W over L over W over L is much smaller than 1. So we will make these two assumptions, and once you do this, you can see that the expression for the input offset becomes VGS minus VT times 1 minus, so root of 1 plus delta ID by over ID becomes 1 plus delta ID over 2ID into 1 minus delta W over L over 2 W over L. Now we can expand the term here, and we will also neglect product of two delta terms. So we will assume, because this is true, we will assume that delta ID by ID times delta W over L over W over L is so small that it can be neglected. So this becomes VGS minus VT into delta ID over 2ID minus delta W over L by 2W over L plus delta VT. So this is of course VGS minus VT by 2 times delta ID by ID minus delta W over L by W over L plus delta VT. Now we realize that the fundamental mismatch is between resistors and between transistors through their VT and W over L. So this particular parameter is not a fundamental mismatch parameter, and therefore we need to extract out delta ID by ID in terms of other fundamental parameters. So I would like to remind you that we derived previously that ID1 R1 should be equal to ID2 R2 by definition, because the output offset voltage should be 0. So this means that ID RD should be equal to ID plus delta ID into RD plus delta RD. So this is ID RD plus delta ID RD plus delta RD times ID plus delta ID delta RD, which we will neglect because it is the product of two terms. Now this implies that delta ID by ID should be equal to minus delta RD over RD. So now this is actually a fundamental mismatch parameter. So now let us go back and plug this in to look at the actual offset voltage of the differential amplifier. So clearly the offset voltage is this expression here. So there are several things to note here. So first of all, the negative signs do not matter, because the mismatches that we are considering mismatches in RD, W over L and VT are independent. In other words, if you were to look at the statistics, there may be some chips where delta RD could be positive, and there could be some chips where delta RD is negative, and same for delta W over L, and these two move in totally independent directions. So what we are actually interested in is the standard deviation of the offset, which we are going to write now. But before doing that, we will just note down one more point, which is that the mismatch in the threshold voltage appears directly at the input. Of the differential amplifier. Now this is quite important. You can see that the mismatch delta VT appears directly without any modification. This means that irrespective of how you design the circuit, the currents and voltages, for example, any mismatch in the threshold voltage would directly appear as an input referred offset. So therefore this is expected to be the dominant term. And finally, you should note that mismatch increases with the overdrive VGS minus VT. Therefore, if you want low input referred mismatch due to RD and W over L, you should try to minimize the overdrive voltage. Now let us try to write down the standard deviation at the input. So sigma squared OS in is VGS minus VT whole squared, VGS minus VT by 2 the whole squared times sigma squared delta RD by RD plus sigma squared delta W over L or W over L plus sigma squared VT. So this is the expression for the input referred offset of the differential amplifier. And as you can see, you expect this to be the dominant component. Since it appears directly at the input. Now, suppose you were to build a single stage op amp. The input, of course, is a differential pair, but you also, instead of a resistive load, you actually have a current mirror. Now, let us see what would happen if you had a one stage op amp. Let us consider only the VT mismatch because that is expected to be most dominant. So, as you might imagine, the input referred offset in the threshold voltage between 1 and 2 directly appears at the input. What about the offset of M3 and M4? It turns out that this offset can also be represented as a series voltage source delta VT 3, 4, and if you look at the input referred component of this, if you look at the output offset voltage and divide it back by the gain, you can clearly see that the input referred offset VOS in would have two components. So the component from 1 and 2 would be directly delta VT 1, 2, but the component from 3 and 4 would be scaled by their relative GMs. I will leave this as a homework exercise for your practice.